When and why would you want to use tabular integration? Well, tabular integration is just integration by parts. So as a first point, the same rules and guidelines apply for how to choose how you're going to set up this process for integration by parts. Namely, still choosing which differentiate integrate is still the same. Right? The points being the thing in the I column you're integrating should be something you know how to integrate. And the overall expression shouldn't get more complicated as you go down this process. The main rule of thumb that I have seen over several years of doing this class for how you choose what to make your differentiation column or your U variable integration by parts, I've seen the acronym of LIATE for how you choose U. For in our case, this is choosing the D column. And you want to pick the first thing on this list you see is what should be the value of U, or the thing you differentiate. And these are logs, logarithms. These are inverse functions. We have algebraic or polynomial functions. We have trig functions and exponential functions. The main idea being here, things that are further to the right, so the T and the E are generally easy to integrate. For trig would mean like sine and cosine. Things that are easy to integrate are on the right. Things that are very hard to integrate or easier to differentiate are on the left, meaning that you want to choose the easier thing to integrate as your I. Because remember, integration is the harder operation here. And so you want to make that part as easy as possible. So putting that to an easy function like a trig, exponential, or polynomial is good. You want to keep the harder stuff like your logs, your inverse trigs to be things that you differentiate. Now, the best use case for tabular integration over just normal integration by parts is when you're differentiating a polynomial. Why? It goes to 0. What does it mean for our choice here? Well, it means that if I want to differentiate A, algebraic or polynomials, I better not see any of these in my problem. Because if they are there, that should be the choice for D and not polynomial. We'll come back to the idea in a little bit in the next video. But if I see any of these, you want to be careful about what you're doing for integration by parts and whether you want to use tabular integration at all to solve the problem. Let's see a more involved example of this idea. Now to work out this integral, x to the 6th minus 3x to the 4th plus 2x minus 1 all times sine of x dx. Now, I do not want to do this problem by normal integration by parts. Why? That's going to require 6 iterations of integration by parts to get that x to the 6th all the way down to a constant so I can integrate the resulting expression. So the clear winner here in this method is tabular integration. Let's set that up. We see based on our setup here, we have a trig function and a polynomial, so I should want to differentiate the polynomial. So we're in a good spot for tabular integration. So let's set up our table. We're differentiating the polynomial, and we're integrating the sine function. So let's fill in this table. We're going to differentiate all the way down until this polynomial goes to 0, which it will after 7 steps, and integrate sine the same number of times. I'm just going to fill that in here, and that's our polynomial side there. For the integration side, we're going to integrate sine of x, which gives me a minus cosine x, not a plus cosine x. We'll put a minus cosine x here, do the pattern on down. We can stop there. Now, from this, we add in our plus and minus signs, and then we can just write out our answer by reading it off the table. So our first term is a polynomial up here, with the term down to the right, the minus cosine here. So that term is that. I get my second term, which is this polynomial here, term down to the right, minus sine of x, with this minus sign up front here. So those two minus signs will cancel, give me a plus term here, like that. And then we just keep going every step down the table, writing out our terms step by step. And we made it to the bottom here. Our last main point will be if I want to do one last integral, it would be the integral of 0 times cosine dx, but that integral of 0 is just a constant, plus c, as there always should be for definite integrals, and that gives us the answer for this problem in a much quicker way than you would get by actually doing out all the different sets of integration by parts. So that is the main use case and benefit for using tabular integration for any sort of problem like this. When you have a polynomial, you can differentiate multiple times to get down to 0. This works out great. Now, the warnings here are exactly what I just mentioned. This works best for when you're differentiating a polynomial. If you are not doing that, the process gets much more complicated. The main sort of difference here, and we'll see this in the next video with these examples, is that you have to keep track of that last integral term. It doesn't just go to 0. And in that case, it might be better off using normal methods as opposed to tabular, but that's up to you to decide. It still works because it is still the same method, but it's more involved and more tricky to see exactly how it works when you're in that sort of scenario. So there is the base and the main use case for tabular integration. It's when you're differentiating a polynomial. We will see in the next video what you can do when that's not the case for a problem.